Let us look at symmetries of an equilateral triangle. So what is a symmetry? It is a transformation such as rotation, reflection, or translation that maps the figure onto itself, preserving distances, angles, and overall shape. Or in other words, a symmetry is an operation that moves or flips a figure but leaves it looking exactly the same as before. So let's take it step by step. We have a triangle which is equilateral, that is triangle ABC. Now a little bit of construction. We take the midpoint of BC as D and connect it to A. Similarly, we take the midpoints of AB and AC and join it to C and B. Now these medians will intersect at G. Now, in case of an equilateral triangle, there are two types of symmetries: rotation symmetry and reflection symmetry. Let's look at the rotation symmetries. There are three of them. If we don't do anything, if we don't do any rotation, that is, in other words, rotating it by 0 degree, we get the same triangle ABC. Now, when we rotate it by 120 degree, so let me rotate it to give you a feel of what I mean by that. This is not a symmetry. This is not a symmetry. No, this is a symmetry. So I've rotated it by 120 degree. So now when we do that, what has happened? C has gone here, A has gone here, B has gone here. Similarly, D has gone here, E has gone here, and F has gone here. So this is the CAB symmetry. So let's do R square on this. So what will happen? First rotation, second rotation. Similarly, first rotation, second rotation. C will go here. Similarly, D will go here. E will go here. F will go here. So it has become BCA. Okay. So those were the three rotational symmetries. Now let's look at the first reflection symmetry. Let's reflect triangle ABC across AD. What will happen? C will go here and B will go here. A will remain where it is, D will remain where it is. E and F will also exchange their positions. E will come here and F will go there. So we get ACB. So the second reflection symmetry is reflection across BE. Now in this case, what will happen? C should go will go to the position of A will come to the position of C. Similarly, D will go to the position of F will come to the position of D. But we don't actually do that. What we do is, whatever existing symmetries we have, we combine them as a composition. So we reflect across AD, which we have already seen. So when we reflect triangle ABC across AD, what will happen? D will go to C, C will go to where B was. Similarly, E will go here and F will go here. So we have done the reflection across AD. Now we rotate it. When we rotate it, A goes here, C goes here, B goes here. Similarly, B goes here, F goes here, and E goes here. So CBA is a reflection across BE. Similarly, the third reflection symmetry is reflection across CF. So here A will come to B, B will come to A, but we don't do it like that. What we do is, first we reflect triangle ABC across AD, and then we rotate it twice. So first we reflect it across AD. So what will happen? C will come here and B will come here. E will come here and F will go there. So we have carried out the reflection. Now we rotate it twice. So when we rotate it twice, what happens? A comes here, B comes here, and C comes here. Similarly, D goes there, F goes here, and E goes there. So we have carried out reflection across AD, and then we have rotated it twice. So here we have done the reflection across CF. F was between A and B. Now F is between B and A. Okay. Now that we have seen all this, we can create a set of all these symmetries. We can say S is equal to a set containing ABC, CAB, BCA, ACB, CBA, and BAC. And we can also write it as a set containing E, R, R square. Instead of S1, we can say S. Instead of S2, we can say R composition S. And instead of S3, we can write it as R square composition S. S is a set of operations on triangle ABC. Or that is with respect to this. With respect to this, we can say S is a set of permutations of the vertices. Let's see whether this forms a group or not. Whether this set under this operation forms a group. So first is closure property. Is it closed under this composition? Remember, here this symbol that I've been using represents the composition of operations, that is carrying out the operations right to left. So A composition B, but when we apply it, we do it the other way around, is equal to C. So one way of looking at it is A is a symmetry in this, B is another symmetry in this. If we do some composition of these two symmetries, do we get another symmetry which is there in this set itself? And the answer is yes. So that means it is closed under this set of transformations. Associative property. A composition B first and then composition with C is equal to A composition with composition of B and C. And if we go through this, this is also satisfied. E does not change anything. That means what? Whatever be the symmetry on which we apply E, that is rotation by 0 degree, does not change the symmetry. It remains as it is. So that means E is the identity. So identity exists. Similarly, let's look at this. What about inverses? Now we rotate it once and rotate it twice more. So when we rotate it once, we come to CAB. When we rotate it twice more, that means R has already been applied. Then we apply R square. What do we get? We get ABC itself. That means we get E. So that means the inverse of R is equal to R square, or we can say R square is the inverse of R. Similarly, a reflection done twice will give us E. That means no change. So S inverse is equal to S. Similarly, so that means inverse exists for every one of these symmetries. Applying R to ABC, we get CAB. Now let's apply S to CAB. We get CBA. Okay, now let's repeat this, but in the other order. We apply S to ABC, we get ACB. And then we apply R to ACB. And it gives us BAC. And here you will notice that these two symmetries are different. Here it is CBA, here it is BAC. So that means it is a non-commutative, we can say, group. Why? Because to say that it forms a group, we just have to show closure property, associative property, existence of identity, and existence of inverse. So this set forms a group under this operation. The only thing is, it is a non-commutative group. This is also called a dihedral group. Why dihedral? Di means two. So we have two types of symmetries, rotational symmetry and reflective symmetry, and applicable to regular n-gons. So this is a regular n-gon. It's a regular triangle, equilateral triangle. And in general, the dihedral group of n sides would contain 2 times n elements. So in this case, in case of this equilateral triangle, there are 2 types of symmetries and we have 3 sides. So 3 times 2, 6 elements should be there, and we do have 6 elements. If it was a hexagon, then we have a regular hexagon, more specifically. Then we would call it as D6, and it would contain 2 times 6 elements, that is 12 elements. So here we can call this as a D3 group, and it is a non-abelian, non-cyclic. In the previous session, we had seen, using the 12-hour clock, a abelian cyclic group. Here we have seen a non-abelian, non-cyclic group. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.